All right, welcome to Unit 1, Function Analysis. This video we're going to talk about analyzing functions graphically. So we've done a ton with the properties of functions, mins, maxes, increasing, decreasing, domain, when their graphs are continuous or not. So I just want to continue that over and actually be able to discuss all those items simply by looking at a graph. So here is a long list of all the different things that by now we should be able to do with a graph of a function. We should be able to look at a graph of a function and know the domain and range in interval notation, of course. We should be able to identify the zeros, which are the solutions or the x-intercepts, and you should be able to find those algebraically as well. Continuity, where is a graph continuous? Which is easier if you think about where is it not continuous. Find the places where it's not continuous, which we've learned about. X values of discontinuities. Again, 3 and 4 kind of piggyback. Like once you realize where you are not continuous, everywhere else is where you are continuous. We talked about increasing, decreasing constant and how to give those as intervals. Vertical and horizontal asymptotes, if there are any, not all graphs have them. Average rate of change between 2 points we've talked about, which is really just the slope of the linear line that connects those 2 points, which is pretty easy. Local and absolute extremas, mins and maxes we've talked about. End behavior, what's the graph doing towards the ends? To the far left, the far right, what's those graphs doing? Which we've hit on a little bit. And then, number 10 is really just don't forget about simple evaluations. Like, hey, if x is 2, where's the function? Tell me, what's the y? What's f of x? Or I guess what would be f of 2. So that should be pretty easy, but I don't want to overlook that. So let's look at a couple graphs. We're going to look at some really interesting weird graphs because the weird graphs, really kind of contain all these things for us to talk about. So here's a really wild graph, but the amount of questions I could ask you based on this graph is, there's just so many, a plethora of different questions I could ask you. So first let's talk about continuity. I think continuity is a big point, right? So we clearly see several places where the graph is not continuous. For example, x equals -8, we see a removable discontinuity. It looks like the point should have been right here, but we moved it up to -3. So it looks like it should have been at -6. The left side is going to -6. The right side is going to -6, but the actual point is at -3. So that's a removable discontinuity. At x equals -2, we also see some type of infinite discontinuity. So again, the left side is at -2, and there is actually a point at -2, but the right side appears to be going up forever towards infinity. So that's interesting. 6 is what we call a jump discontinuity. So the left side is down at 2, the right side is up at 5, and that's creating a jump. They're not coming together, so that's a jump discontinuity. So, those are kind of the cool things to look at in terms of discontinuity. So if I were to ask you to write the domain of this function, okay, we'd have to skip all those discontinuities. We have to make sure those discontinuities get skipped. So it'd be pretty, not hard to write. We'd have to be able to write that out. Other things we could talk about are where the zeros, where the solutions. Looks like -11, -4, and 10 are solutions. Kind of easy there. This arrow right here signifying that it's going up forever, and this arrow right here, assuming that it's going down forever, means that there are no absolute mins or maxes, but we do see, like right here, this value right here would be a relative maximum. This value right here would be a relative maximum. I would not call this a relative min because, again, it was a displaced point. It was a removed point. Even though it looks like a relative min, it really would not be one because of the discontinuity going on there. So, again, lots of different things that I could ask you to do. And, again, don't forget simple things. Like I could say, hey, what is f of 2? When x equals 2, where's the function at? And that's just as simple as looking. 2 looks to be at 3. So f of 2 equals 3. So that's pretty easy to do. Increasing, decreasing. Again, there's a lot going on here to talk about increasing, decreasing, but from -infinity to -8, it is decreasing. Looks like from -2 to maybe -0.2. I mean, that's kind of a guessing point right there, exactly what that x value is. We're decreasing. We're decreasing again from this max of, which occurs at maybe 2.8. Again, sometimes there's guessing games. You got to guess a little bit with these graphs in terms of what the x values are. And again, to 6, it's decreasing. It's decreasing again. Looks like this would be 7 on the x-axis, 7 towards positive infinity. So it's decreasing lots of places. It doesn't appear to ever be constant. I don't see it being straight line at any point. Where's it increasing? It's increasing from -8 to -2, clearly increasing. It's increasing from about, again, -0.2 to maybe 2.8, somewhere in there. You could see that the graph is increasing. And it's also increasing, again, from 6 to 7. In a very small area, the graph is increasing right there. Again, so I'm just trying to, talk about this graph and realize there's really lots that we could talk about in terms of what we see in this graph. So be able to kind of, be able to just answer some basic questions, when you see a weird looking graph like this. Here's another one. Maybe not as weird, but still pretty weird. We see several discontinuities. -2 is a discontinuity. -1 is a discontinuity. +1 is a discontinuity. And if I were to ask you to name those, -2 would be removable because it looks like the point just simply got moved. It got removed and put somewhere else. At -1, that's a jump. The left side's 3, the right side's at 1. And at 1, that's an infinite discontinuity because the sides are going up forever and ever. If I were to ask you to give me the domain, we would make sure we need to skip any values that don't exist. So the domain would be -infinity to -1. Again, because at -1, no point exists. Now you might say, well, whoa, wasn't I supposed to skip -2? Well, no, there is a discontinuity at -2, but there is still a point. There is a point at -2. It's just removed, but it's still there. So therefore, it is in the domain. -2 is in the domain since there is clearly a point at -2. But -1 has no point. Like if you look there, there is no point at -1. And then I also would continue on from -1 to +1. At +1, again, there is no point. It's an asymptote. It looks like it's going up forever. And then again, I am also continuous from 1, looks like towards infinity as well. So there's the domain. Let's talk about end behavior here. So again, when I'm talking about end behavior, I'm looking at the left end and the right end. So one way to talk about end behavior is to say, okay, as x goes towards -infinity, so as x goes way to the left, look, where's the function going? Where's the function going? And it clearly looks like the function is going up forever towards infinity. And that makes complete sense, right? This arrow is pointing up forever. So as x goes way to the left, -infinity, the function looks like it's going up forever. And then the right end behavior is a little bit different. As x goes towards +infinity, so as x goes way to the right, the function looks like it's getting limited, possibly due to a horizontal asymptote at 0. Notice that this arrow looks like it's starting to slowly level off. And it looks like it's never, ever going to cross 0. It's just going to get really, really, really close. And that's kind of something you got to realize by being able to look at the graph and sense that that's happening. If I clearly wanted you to see that that arrow was going down forever, I would have clearly had it cross the x-axis and point way down. But it's not. So that's kind of a horizontal asymptote there at 0, where as we move to the right, the function is actually slowly going towards 0. So a lot of cool things that we could see in this graph. Here's a graph of a rational function, x plus 2 over x minus 4. And, this graph is maybe not a ton going on here as we've seen the previous graphs. But one issue we clearly see is at +4. There's clearly a discontinuity at +4. It's an infinite discontinuity. Right side's going up, left side's going down. And furthermore, if we look at the denominator, it's no surprise that x cannot be 4 because if you plug it in, you get zeros. That's a discontinuity. But every other place looks good. So the domain would be -infinity to 4 and then 4 to infinity. So every other x value does exist except for 4. We can talk about mins and maxes. There aren't any, right? Because these arrows are going up forever and down forever. So there's no absolute mins or maxes. What about end behavior? What's happening to the ends of this graph? And this is what we talked about in the asymptote. So if I look to the left and to the right. So let's look at as x goes towards -infinity, way to the left. It does look like the graph is starting to level off, and I got to figure out where. And then the same thing with as x goes towards infinity. If I go way to the right, and again, it does look like this red graph is starting to level off. Now, how do I figure that out? Well, you remember we learned in previous video of our asymptotes how to find horizontal asymptotes. The degree of the numerator is 1, the degree of the denominator is 1, and when the degrees are tied, there's a horizontal asymptote, and you can find it by looking at the leading coefficients. So the leading coefficient in front of this x is 1, the leading coefficient in front of this x is 1, so divide the leading coefficients, and there is a horizontal asymptote at positive 1. And that actually makes sense. Once you draw it in, you could clearly see, oh yeah, I see that this red line is starting to level off from the bottom as we go to the left and from the top as we go to the right. But either way, the function is starting to level off at 1 as we look at the ends of the graph. And that's due to the horizontal asymptote that the function's never allowed to cross. It's never allowed to cross that horizontal asymptote. So that's why the function towards the ends is limited to that horizontal asymptote of 1. Here's another cool graph. This is a square root with a quadratic inside of it. So one cool thing you could do is to find the zeros, you could set the inside equal to 0 and solve. And you have to factor a little bit here, but it doesn't take too much work to factor. So we do see 2 zeros at x equals 0 and x equals 2. And again, that comes from knowing how to solve a quadratic. So we actually do have 2 absolute mins. There is no values lower than 0 and 2, so those would be considered absolute mins. The domain would be negative infinity to 0, and then 2 towards infinity. It's clearly, there's a big break from 0 to 2. There's nothing there. It doesn't exist. And if you want to know why, it's because values in between 0 and 2 create a negative in a square root, which you're not allowed to have. So if you don't believe me, just plug in 1. For example, if I try to figure out what is f of 1, the square root of 1 squared is 1, minus 2 times 1 is 2, and 1 minus 2 is negative 1. And you can't have a negative in a square root. So that's clearly why there's nothing going on in between there. So does this graph have any discontinuities? Technically, no, which is a little confusing to understand, but there is an area of the graph where the domain doesn't even exist. So when we talk about discontinuities, we talk about values within the domain that have problems or issues. And within the domain of negative infinity to 0 and 2 to infinity, we don't have any problems. Where the domain doesn't exist, there's clearly a lot of problems because nothing exists there. So hopefully that kind of makes sense as well. Where is this graph decreasing? It's decreasing from negative infinity to 0. So as I follow this, it's always decreasing. Again, that's from negative infinity way to the left all the way to 0. Those are the x values where the graph is going down. And then the graph is increasing from 2 to infinity. So on this side, the graph is going up towards infinity. So it's increasing from 2 towards infinity. What else can we ask you here? Let's talk about that end behavior again. As x is going towards negative infinity, it does appear the graph is continuing to go straight up. So the end behavior would be infinity. So as we look to the left side of the graph, the function is going up forever. And if we look to the right side of the graph, the function is also going up forever. So as x goes towards negative infinity, the function goes towards infinity. And again, we could see that up here. And then likewise, as x goes towards positive infinity, the function goes towards positive infinity as well. And we could see that up here. So again, lots of cool things that I could ask you. I mean, I doubt I'm ever going to ask you every single characteristic of a function for one graph. But, if one graph has a lot of cool features, then I'm definitely going to ask those things more than likely. Okay. Now, since we're on the topic of talking about graphs, there's a couple basic graphs that you should know. Basic functions, right? We actually call these parent functions. Okay, because these are 11 basic functions that really kind of form many, many, many graphs. And that's what parents do, right? Parents form many, many kids. So we call these parent functions because they're kind of like the most basic functions that create many different functions in other graphs that we may see. There are more than 11. I'm going to be honest. These are 11 that we're going to focus on. 8 of them you should be fairly familiar with, and 3 of them are going to be pretty new. So let's start taking a look at them. This is the identity function. This is a linear function. The linear functions are known as identity functions. And the interesting fact here is that this is the only function that acts on every real number by leaving it alone, which is why it's called the identity function. Because if you plug in 2, you get 2. If you plug in 3, you get 3. It's like looking in a mirror. Right? The input and the outputs are always going to be identical, which creates a linear graph, right? So it's a very, very simple function, very easy, what everybody knows about. Here's another one. This is called the squaring function, or you may know it as the quadratic function. It creates a parabola. Interesting fact is that it's a parabola and has a reflective property that is useful in making flashlights and satellite dishes. So, the science and the math behind how to make a flashlight and a satellite dish involves understanding quadratic functions. So this is x squared. So x squared is one you guys are very, very familiar with. Here's the cubic function, x cubed. The origin, the interesting fact here is the origin is called the point of reflection for this graph because the graph changes curvature at that point. So what we mean by that is notice that the graph, on the here's the origin right here, 0, 0. On the left side of the origin, it's called concave down. It's curved like this. That's called concave down. It's curved down. Whereas on the right side, it's curved up. We call that concave up because the curve is going up. So that is something cool about the cubic function is that at the origin, it switches the curvature of the point. That curvature is a cool calculus topic that you'll learn about. Here's a square root function. Remember, you cannot have negatives in square roots. So that's why the basic parent function, the square root of x, nothing exists to the far left. There's just nothing over here because you're not allowed to plug negatives into square roots. Or at least you're not allowed to end up with a negative inside of a square root. Now, here's a cool fact. Just put any positive number into your calculator, then take the square root, then take the square root again, then take the square root again, and so on and so on. And eventually, you will always get to 1. Now, it takes a while. Like, even if you do the square root of 4, and then the square root of that, and then the square root of that, and the square root of that, you eventually do get down to 1. Sometimes you're going to get a ton of decimals for a while, but it always goes down to 1. And that's with any positive number. Square root functions are pretty cool. They're pretty basic. They do increase forever, even though it's a pretty slow process. They do continue to go up forever and ever and ever. Here's a reciprocal function. A reciprocal function is 1 divided by x, which creates a rational function. All rational functions are built on this basic parent function. This cool, interesting fact is that it's called a hyperbola. Maybe you've heard that before or not. But hyperbolas are also very useful mathematical functions that are used in satellite dishes. Even satellites that are sent up in outer space do a lot with hyperbola, which are reciprocal functions as well. So they're pretty cool, simple functions as well. And they do have an asymptote. You'll notice that there's both a vertical and a horizontal asymptote. There's clearly a vertical asymptote at x equals 0 because x cannot equal 0. That puts a 0 in the denominator. But because the numerator is 1, it will never, ever be 0. And since the numerator can never, 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 never be 0, then the function can never, never, never be 0, which is why there is a horizontal asymptote at the x-axis, or y equals 0 as well. So cool function there. This is the exponential function. And the example I have here is e to the x. Now, to be honest, remember, e is just a number, right? It's a very standard number. It's an irrational number. It's kind of like pi. That shows up in a lot of applications. The symbols e and pi were both brought into popular use by the great Swiss mathematician Leonhard Euler. He's the one that kind of founded these symbols for these irrational numbers. But it doesn't have to be e. That's just the one I chose for this picture. You could do 2 to the x, 3 to the x, 4 to the x. I mean, any positive base, even 1/2 to the x could be used, or 1.3 to the x. The point is that the exponent is the x. And these create some exponential growth. Or if your base is between 0 and 1, it's actually a decay. And I could draw you a quick picture of that. So if you have a base like 1/2 that's less than 1 but greater than 0, then you are actually at exponential decay, where the graph is decreasing from left to right. Whereas exponential growth, like you see here in this picture, is increasing from left to right. So those are cool functions too. Logarithmic functions are one you should be familiar with, but unfortunately not every kid is. Remember, you can have any base, kind of like I just went over with exponential. The base could really be anything. Same thing is true with logs. So this is base e, but you could do base 10, which would just be log. You could do base 2. You could do log base 3. But the important thing is that we always leave the x alone for the parent function. And the graphs are kind of cool. There's actually a vertical asymptote at x equals 0. That's because if you remember the properties of logs is you cannot have a 0 inside of a log of any type, and nor could you have negatives, which again is why there's nothing over here on the negative side. There's nothing on the left side of the graph because you cannot plug a negative value inside of a log of any type. So this function increases very slowly. I think this is actually one of the coolest facts. This function increases very, very slowly, but it does always increase. And here's an example to prove how slow it is. If the x and y axes were both scaled with units of 1 inch, so if the x and y axes were 1 inch, 2 inch, 3 inch, 4 inch, 5 inch, and so forth, you would have to travel more than 2.5 miles, 158,400 inches along the curve just to get to 1 foot or 12 inches above the x-axis. So think about that. If these were all considered 1 inch, 12 inches would be maybe up here somewhere, right? Let me use a brighter color so you can see it. Maybe 12 inches would be up here somewhere, right? Or maybe a little bit higher. But it would take an x value of 158,400 just to get up to 12 inches. So this function moves very, 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 very slowly, but it is always increasing. It just takes forever. So I think that's kind of a cool feature. But it is always increasing. Here is an absolute value function. We see this sharp V. That's the instant sign of an absolute value function. And that is just the absolute value of x. You could use the absolute value bars, or you could just write ABS. The function has an abrupt change of direction or a corner at the origin, while all other basic curves are considered smooth, meaning that any turns are smooth curves. So an absolute function is the only function we're going to ever look at that has that, that abrupt sharp change, a sharp corner. So it's kind of a cool function. And here's one that I bet you've never seen before, but we're actually going to use this a lot when we get into Unit 2. This is called a logistic function. It has two asymptotes, two horizontal asymptotes, which is pretty rare for a function to have. But there's a horizontal asymptote at y equals 0 and at x equals 1. And the graph curves in between. And notice again, right here at 0, 0.5, it changes from concave up. And then on the right side, it's concave down. Again, concave up and then concave down. So first off, this is a really interesting function. It's not one that I really expect you to know at the top of your head. It's definitely one of the newer ones, but it's really a weird looking function. It's 1 divided by 1 plus e to the negative x. So it's a crazy function, but in business and biology, this function has so many crazy applications. And we're even going to do an example with COVID-19 where this logistic curve has a lot to do with it. Here are two more functions that you might be somewhat familiar with, but we're going to cover them a ton in Unit 3. This is the sine function, sine of x. I don't want to talk too much about it right now because we're going to cover a ton of it in Unit 3, but it's a really cool function. This function and the sinus cavities in your head actually derive their names from a common root, the Latin word for bay. But due to a 12th century mistake made by Robert of Chester, what a cool name, Robert of Chester. I wish I was Michael of Twinsburg. But anyway, he translated it incorrectly from an Arabic manuscript. So we call it sine, but maybe it should have been bay x. Okay, but anyway, kind of a cool, interesting fact there. And here's cosine. And again, it's okay if you're not so familiar with the cosine curve. We're going to cover it in depth in Unit 3. But the cool fact here is the local extrema of a cosine function is at exactly the same spot of zeros of the sine function. So if you were to put the cosine function and sine functions on top of each other, the maxes for cosine are the zeros for sine and vice versa. But anyway, we're not going to deal a ton with those functions until later on. Now, why I introduce you to these 11 functions is because, I want you to just be familiar with what they look like, both algebraically, written as a function, and graphically, looking at a picture. And what we're going to do moving forward is really talk about how we can, learn from these graphs. And I want to be able to understand mins, maxes, domains, asymptotes. Hey, where are the zeros? Can you find the zeros by the graph? Can you find the zeros algebraically? Where's the graph increasing? Where is it decreasing? Those are all kind of cool things that we could talk about with all of these graphs. So as we move forward, as I ask you these questions, all these 10 questions about functions, continuity, all the fun stuff, I should be able to, show you any of these graphs of any type, and you could kind of understand all the different characteristics of them. And it's going to take some practice for sure. We're not going to be able to master it all right now, but as we move on, we'll become really good at it, and it'll be super fun. All right, that's it for this video. Hope you learned a little bit about functions and their graphs.